A Roman aqueduct stands intact after two. A modern bridge down the road is already falling apart. The difference is not just in the stones, but in the forgotten glue that holds them together. This is the mystery of ancient mortar, a lost alchemy of construction that gave buildings the power to outlast empires. By the end of this, you will hold the key to why these recipes worked and how they could revolutionize our future. What secret ingredient allowed Roman concrete to heal its own cracks? Why did medieval masons mix egg whites and beer into their walls? We are about to decode the material science that built the ancient world. What forgotten wisdom from the past could fix the problems we are building for tomorrow? Think of modern cement as a rigid, brittle command. It demands perfection from the start and offers no forgiveness later. Ancient mortar was something else entirely, a patient conversation between material and environment. This fundamental distinction begins with its very definition. When we speak of ancient mortar, we are not talking about product. We are talking about a philosophy of construction, a localized alchemy that transformed whatever the earth provided into something greater than the sum of its parts. From the volcanic ash mortars of Rome to the sticky rice-lime composites of Ming China, these were bespoke recipes, crafted for specific places and purposes. The builders understood that a wall was not a dead barrier, but a living skin for a structure. It needed to breathe, to flex with the ground as it settled, to interact with the rain and the air. Their mortar was designed to be a participant in that relationship, not a dictator. This is why the Pantheon's dome still stands, a perfect hemisphere of concrete, while countless modern parking garages require constant repair. The ancient material was engineered for resilience through flexibility, for a long life of graceful aging. It was a component of an ecosystem, meant to last for generations, quietly strengthening through chemical conversations we are only now beginning to fully translate. This adaptive intelligence, baked into the very paste between the stones, is the profound departure point from our own industrial approach. The secret to this conversation started with fire and patience. The first universal ingredient across nearly every ancient civilization was lime, but not as we know it today. This was not a powder scooped from a bag. This was a material born from a transformative ritual. It began with limestone, pure calcium carbonate from ancient seabeds, placed into a kiln and heated to a blinding white heat. This process, called calcination, drove off carbon dioxide and left behind a caustic, volatile substance known as quicklime. In its raw state, quicklime is dangerous, capable of violent reactions. The true artistry began in its taming. Builders would carefully add water to the quicklime, a process called slaking, which released tremendous heat and steam, yielding a wet paste known as lime putty. And here is where ancient wisdom diverges completely from modern efficiency. Today, this paste might be used within days. In the ancient world, the best masons treated time as their most potent ingredient. They would bury this lime putty in deep pits, sealed from the air, and leave it there, not for weeks but for years, sometimes for decades. This was the lime revolution, a slow alchemy of maturation. During those long years of rest, a remarkable transformation occurred. The particles of lime continued to react with residual water, breaking down into an impossibly fine, almost creamy consistency. Think of it like a fine wine aging in a cellar, or a sourdough starter developing complex depth over years of care. This aged putty became profoundly reactive and plastic, meaning it could be worked and shaped with an almost buttery smoothness, filling every microscopic crevice in a stone. When it finally went into a wall, it carbonated slowly, pulling carbon dioxide back from the air to reform a rock-like bond, but one that was incredibly dense and cohesive. The Romans elevated this to a high science. Their lime putty was the secret behind the flawless curves of their arches and the enduring strength of their harbor concrete, which had to set underwater. They understood that the quality of the glue dictated the destiny of the structure. This patient, deliberate cultivation of a single material stands in direct opposition to our world of just-in-time production. We prioritize speed, they prioritized permanence. The lime that spent years resting in the dark earth was preparing for a lifetime, centuries long, holding the light of the world. Yet lime alone, no matter how patiently aged, was not the complete answer. The true revolution, the leap that turned durable mortar into seemingly immortal concrete, came from a second, almost magical ingredient. Builders across the ancient world stumbled upon a profound secret. When you mixed that slaked lime with certain fine, sandy powders of volcanic origin, or even crushed, fired ceramics, something extraordinary happened. The mixture no longer just dried, it underwent a chemical metamorphosis. It could set rock hard, even underwater, and its strength did not peak in a few weeks. It grew quietly for centuries. The Romans had a name for this wonder powder, Pozzolana, sourced from the volcanic hills around. For them, it was the key to empire, allowing them to build harbors that the sea and aqueducts that conquered mountains. But this was not a Roman monopoly, it was a global discovery. In the Middle East, masons pulverized old bricks and pottery, creating a reactive powder that gave Islamic architecture its legendary arches and domes. In ancient Asia, builders utilized rice husk ash, a waste product from farming, to create mortars of incredible resilience. Each culture, using what their local environment provided, had independently unlocked the same material science principle. These powders, which we now call, are rich in silica and alumina. When mixed with wet lime and water, they begin a slow, silent conversation. They react to form a web of interlocking crystals known as calcium silicate hydrate. This is the same glue that gives modern Portland cement its strength, but here is the crucial difference. In modern cement, this reaction happens quickly and then largely stops. In mortar, the reaction is slow, fed by the silica in the over decades and even centuries. This continuous, low-level crystallization does something miraculous. It allows the material to fill its own tiny voids and micro cracks. Imagine a wall that possesses a faint, persistent memory of its original liquid state. When a hairline fracture forms from stress or settlement, moisture seeps in, carrying dissolved lime and silica. This reawakens the chemical process, depositing new crystals that literally knit the crack back together. The mortar does not just resist decay, it actively heals itself. This is why Roman concrete marine barriers, pounded by for 2,000 years, are often stronger today than when they were poured. The very agent of erosion, water, becomes the catalyst for repair. Our modern concrete, in contrast, is designed to be inert and static once set. A crack is a terminal diagnosis, a point of failure that only widens. Ancient mortar was designed to be dynamically alive, engaged in a perpetual dance of dissolution and reformation with the world around it. They did not build against nature, they invited nature to become a co-builder. But the most enigmatic chapter in this recipe book is written not in stone, but in substances once alive. Scattered through medieval manuscripts and oral traditions are instructions that seem to belong in a kitchen, not a construction site. To strengthen their mortar, some masons would stir in animal blood. Others swore by fresh egg whites, or lumps of cheese left to curdle, or even barrels of stale beer. To the modern ear, this sounds like pure superstition, the kind of folk magic that surrounded great building projects. Yet what if these were not rituals, but sophisticated, if intuitive, chemical formulas? modern laboratories are now revealing a startling truth. These organic additives were functional ingredients, a lost branch of materials science that blended domestic wisdom with engineering. Take egg whites, rich in a protein called albumin. When whipped into a lime mix, albumin can act as a natural plasticizer, making the mortar more workable and sticky, helping it cling to vertical surfaces. More importantly, it can entrain microscopic air bubbles throughout the paste. These tiny pockets act as expansion chambers, giving the mortar room to flex when water freezes inside it, preventing the destructive cracking that plagues modern masonry in cold climates. Casein, the protein in milk and cheese, behaves similarly, but also influences the very architecture of the curing mortar. It can guide the growth of the calcium silicate hydrate crystals, encouraging them to form a denser, more interlocked and tougher microstructure. Think of it like the difference between a haphazard pile of twigs and a carefully woven basket. The basket is far stronger, and the organic additives helped weave that basket at a microscopic level. These builders, without knowing a thing about proteins or polymers, were manipulating matter on a nanoscale. They observed that a mortar mix with egg white dried smoother and lasted longer through winters. They saw that a batch tempered with beer seemed more resilient. They were conducting generations-long experiments, passing down the recipes that worked. This represents a profound intimacy with material. The builder's pantry and the mason's yard were not separate worlds. The same understanding of how egg whites thicken a sauce, or how beer ferments, informed how they made stone defy gravity and time. It was a holistic science, one that saw no divide between the organic and the inorganic, between the home and the monumental. This knowledge, so deeply embedded in craft and tradition, evaporated with the arrival of industrial standardization. A bag of Portland cement needs no cheese, no eggs. It promises consistency, but in gaining that predictable simplicity, we severed a deep, intuitive connection between the builder and the very life of the material. We traded a complex, adaptive recipe for a simple, brittle one. The ghosts of those old formulas whisper a question. What other profound material truths did we forget when we stopped looking to the kitchen for the secrets of eternity? This chemical conversation reaches its most spectacular expression in the itself. To understand the true genius of ancient material science, we must look not to the hills, but to the sea. The Roman harbor at Caesarea stands as the ultimate testament. Built by Herod the Great 2,000 years ago, its massive concrete breakwaters were poured directly into the Mediterranean. Today, those same blocks endure, encrusted with life but uncracked by time, while modern concrete nearby crumble into the surf after mere decades. This is not a story of simple durability. It is a story of a material engineered to use its greatest enemy as its source of strength. The Romans achieved this by designing a concrete that did not merely resist seawater, but actively required it to reach its full potential. Their formula was deceptively simple. They combined that slaked lime putty with a specific volcanic ash, Pozzolana, and then added large, fist-sized chunks of local rock. This coarse aggregate was not just filler, it provided a robust internal skeleton. But the magic truly began when this mix met the ocean. For modern Portland cement, seawater is a corrosive soup. Chloride ions attack the steel reinforcement, causing it to rust and expand, which cracks the concrete from the inside out in a process called spalling. Roman concrete had no steel to corrode. More astonishingly, the seawater initiated a beneficial, long-term chemical reaction. When the lime and volcanic ash mixture was submerged, it acted as a powerful catalyst. It triggered a hot, slow-forming reaction that created incredibly stable and rare minerals, most notably aluminous. Think of this mineral as the ultimate architectural crystal. It forms as tiny, plate-like structures that interlock with a fierce, almost unbreakable bond. This crystallization process does not stop after a month or a year. It continues for centuries, fed by the steady interaction with the seawater's chemistry. The concrete does not just sit there, it gradually densifies and strengthens from the inside out. The very agent that destroys our modern structures became the lifeblood of the Roman ones. This flips our entire understanding of a hostile environment on its head. We spend billions trying to shield our infrastructure from the elements, to make it inert and isolated. The Romans designed theirs to be an open system, to engage in a productive chemical dialogue with the world. The harbor at Caesarea was not fighting the sea, it was collaborating with it. Each wave over was not an assault, but a gentle stir of the mixture, encouraging the slow growth of a stronger, more resilient stone. This case study forces a humbling question. Have we, in our quest for total control over our materials, fundamentally misunderstood how to build things that last? Our concrete is designed for a short, predictable life in a controlled setting. Theirs was designed for an open-ended future in a dynamic world, becoming not a relic of the past, but a living lesson from it. The silent conversation within Roman seawater concrete was a masterpiece of material dialogue, but the same principles would later reach for the sky. Centuries later, across medieval Europe, an entirely new architectural language was being born, one of impossible height and walls of colored light. The Gothic cathedral did not just challenge gravity, it seemed to defy the very nature of stone. But these soaring vaults and delicate tracery were not held aloft by faith alone. They were pinned to the heavens by a precisely formulated glue, a mortar whose recipe was as critical to the vision as the architect's plans. Where Roman engineering conquered the horizontal plane of the sea, Gothic craft mastered the vertical ascent. The builders of Chartres, Dame, and Canterbury faced a problem of terrifying delicacy. Their designs called for thinner walls, larger windows, and intricate stone webs that met hundreds of feet in the air. The mortar between each stone block became the most critical joint in the entire skeletal structure. It had to be strong, yet flexible. It had to set predictably, but not too quickly, allowing masons time to adjust the precise alignment of complex ribs. And it had to shrink minimally as it cured, or the entire delicate balance of compressive forces would be lost, leading to catastrophic cracking. Their solution emerged not from a laboratory, but from the rubble of older buildings. They began incorporating finely crushed brick dust and fragments of old pottery, a material known as. This was not mere frugality or recycling. It was a calculated rediscovery of chemistry. The fired clay, rich in silica and alumina, acted just like the Roman volcanic ash. When mixed with their lime putty, it created a hydraulic mortar that could set in damp conditions, and most importantly, developed strength slowly and steadily. This controlled cure was everything. Imagine the scene high on the scaffolding. A team of masons is fitting the keystone into a towering rib vault. The mortar must be workable for hours, allowing for minute adjustments with wooden mallets and levels. Then, over the following days and weeks, it must gain strength uniformly, without pulling away from the stone as it dries. The mixture ensured this. It reduced shrinkage dramatically, creating a perfect, full contact bond that distributed the immense weight of the roof down through a filigree of stone. Each cathedral was a decades-long experiment in structural chemistry, with the mortar recipe being a closely guarded secret of the lodge. The master mason knew that the wrong mix, one that set too fast or shrunk too much, could mean the difference between a vault that stood for centuries and one that collapsed before the scaffolding was even removed. This empirically derived knowledge, passed down through apprenticeships, represented an intimate, hands-on understanding of material behavior. They may not have spoken of calcium silicate hydrates or reactions, but they knew that the pink dust from old roof tiles made the mortar grip better and last longer. Their genius was in applying an ancient material principle to a new, audacious purpose. The Gothic cathedral is often celebrated for its spiritual aspiration, for its light and verticality. But that light pours through windows held in place by stone, and that stone is held in place by a forgotten, gritty paste of lime and crushed brick. The true miracle is that this humble, recycled powder gave solidity to the sublime, allowing faith to be written in stone and glass, a testament to the enduring power of a perfectly tuned recipe. While Gothic masons were recycling brick dust in Europe, a different kind of alchemy was taking shape in the East. In ancient China, master builders perfected a mortar recipe that sounded more like a dessert than a construction material. To bind the stones of their most important structures, from the mighty walls of Nanjing to sacred tombs and graceful pagodas, they stirred in a thick, glutinous soup made from sticky rice. This was not a ritual offering, but a calculated and brilliant stroke of materials engineering. The resulting paste, an organic-inorganic composite, created some of the most durable masonry the world has ever seen, and modern laboratories have only recently decoded its secrets. The key lies in a complex sugar molecule called amylopectin, which gives sticky rice its characteristic glue-like texture. When this rice soup was mixed with slaked lime, something remarkable happened at a microscopic level. The long, branching chains of the amylopectin did not just sit there, they actively participated in the mortar's crystallization. Think of these organic molecules as a vast, intricate scaffold or a template. As the lime began to react with carbon dioxide from the air to form calcium carbonate, the rice amylopectin guided and controlled that growth. Instead of forming large, brittle crystals that could easily crack apart, the calcium carbonate was encouraged to precipitate as a dense, interlocked mass of incredibly tiny crystals. The result was a composite matrix that was compact, waterproof, and remarkably resistant to both physical weathering and biological attack. Few microbes could break down this stony, rice-reinforced paste, which helped prevent the organic decay that often undermines structures. This was sustainable biocomposite technology, perfected over 1,000 years ago. The builders used a staple food crop to create a mortar that was simultaneously stronger, more flexible, and more resilient than lime alone. It was a harmonious fusion of the agricultural and the architectural, turning a household ingredient into the guardian of empires and dynasties. Today, material scientists in labs are striving to replicate this ancient wisdom, designing new composites with polymers that mimic the scaffolding effect of sticky rice. Yet the original formula stands as a quiet monument to a different kind of knowledge, one that saw no boundary between the pantry and the palace, and that understood how to weave the very threads of life into the fabric of stone. Yet this global library of material wisdom did not vanish in a single catastrophe. Its loss was a quieter story, a slow forgetting caused not by fire or invasion, but by changing priorities. The first great rupture came with the decline of the empires that had been its greatest patrons. When the administrative machinery of Rome faltered, the intricate trade networks that supplied specific volcanic ashes across the Mediterranean frayed. The deep generational knowledge held by specialized guilds, the masons who knew how long to age a lime putty or which local clay made the best, became fragmented. This was not a loss of instructions from a single scroll, but the dispersal of a living, hands-on tradition. Cathedrals still rose, but the recipes became more localized, more variable, passed down as oral secrets that grew fainter with each generation. The true death knell, however, arrived with the age of steam and iron. The Industrial Revolution redefined progress itself, and its new gods were speed, uniformity, and scale. In the early 19th century, the invention of Portland cement offered the perfect embodiment of these values. Here was a material that could be manufactured anywhere with the right limestone and clay, that set with predictable speed, and whose strength could be calculated on an engineer's slide rule. It represented control. The messy, location-specific alchemy of ancient mortar, with its years-long slaking pits and its reliance on peculiar local ashes, seemed hopelessly archaic. It was inconsistent. It was slow. It was, in the relentless calculus of industrialization, uneconomical. A builder could not tell a railroad baron that a bridge pier needed 3 years for its mortar to mature properly. So the old craft knowledge was not so much disproven as deliberately sidelined, relegated to the realm of historical curiosity or quaint folklore. The subtle interplay between organic additives and mineral chemistry, the intimate understanding of how a mortar should breathe with its environment. These were not deemed worthy of preservation in the new scientific curricula. We traded a deep, adaptive wisdom for a shallow, universal convenience. In standardizing the world, we paved over 1,000 different paths to permanence. The forgotten mortar recipes did not fail. We simply stopped listening to what they had to say. So what does this ancient wisdom reveal about the material that surrounds us today? Modern concrete is an undeniable triumph of engineering ambition. Its invention unlocked the vertical city, the sprawling bridge, the vast dam. It gave us the ability to mold the very skeleton of civilization with a speed and scale the ancient world could scarcely comprehend. This material, built around Portland cement, possesses a phenomenal compressive strength, meaning it can bear immense weight without crushing. It is the reason skyscrapers can climb into the clouds and why highway overpasses can support endless streams of traffic. But this formidable strength comes with a hidden and fundamentally different personality. Where ancient mortar was designed for dialogue and flexibility, modern concrete is engineered for silent, rigid command. Its strength is gained with astonishing speed, often reaching functional capacity within a mere 28 days. This rapid set is perfect for the economics of modern construction, but it locks the material into a brittle, crystalline state. Imagine the difference between a young, green sapling and a pane of glass. The sapling can bend in a fierce wind, its fibers flexing and absorbing the energy. The glass pane stands rigid until the pressure exceeds its limit, and then it shatters. Modern concrete behaves more like the glass. It has little innate tolerance for movement, for the subtle shifts of the earth, for the expansion and contraction caused by temperature swings. This inherent brittleness inevitably leads to the formation of hairline fractures invisible to the naked eye, but vast enough on a molecular scale. And these tiny flaws are not benign. They become highways for invasion. Water seeps in, carrying with it dissolved salts, particularly chlorides from icing agents or sea air. In reinforced concrete, which uses steel rebar for tensile strength, this is where the trouble truly begins. The chlorides attack the steel, causing it to rust. Rust occupies more volume than the original steel, so it expands with tremendous force from within the concrete, cracking it apart from the inside in a destructive process often called concrete cancer. This is the paradox of our modern built environment. We have created structures of immense short-term strength that contain the seeds of their own long-term decay. The material is not designed to heal, but to slowly succumb. It is often measured in decades, a planned obsolescence written into its chemical code, standing in stark contrast to the long conversations still being held by the stones of the Pantheon or the of Caesarea. We built a world for the present, with a strength that is spectacular, yet silent and ultimately fragile. This silent, ongoing repair is perhaps the most profound secret of all. While modern concrete demands constant vigilance and intervention, ancient mortar possessed a quiet, internal intelligence. It could heal itself. This phenomenon, known as autogenous healing, transforms our understanding of what a building material can be. Imagine a hairline fissure, thinner than a thread, appearing in a 2,000-year-old Roman wall after a minor tremor. To our eyes, it is a flaw, the first sign of decay. But to the chemistry of that ancient mortar, it is an invitation. Moisture from rain or humid air seeps into that microscopic canyon. Within the mortar, there are still tiny particles of lime or dormant for centuries. The water awakens them. Dissolved lime travels into the crack, where it meets carbon dioxide from the atmosphere. Slowly, imperceptibly, a new mineral begins to form. Calcite crystals, the same building block of limestone and marble, start to grow. They do not grow in a random, chaotic way. They precipitate precisely within the void, interlocking with the existing material, gradually filling the gap from the inside out. It is a process of geological patience, taking years or even decades to complete a repair we would never notice. The crack is not just patched, it is literally turned back into solid stone. This is not a metaphor for resilience. It is a literal chemical mechanism of self-repair engineered into the material from the very beginning. The builders did not need to understand the crystalline chemistry to observe its effects. They saw that their structures endured through earthquakes, frosts, and floods that should have shattered them. They crafted a material that was not a finished product, but a starting point for a conversation with time. Our modern concrete, in stark contrast, is designed to be chemically inert once it sets. Its reactions are meant to be complete within weeks. A crack is a terminal failure, a breach in the system that only widens as water and salts invade. We respond with external patches, epoxy injections, and costly replacements, a cycle of maintenance that treats the symptom but ignores the root cause of a static, brittle material. The ancient paradigm was fundamentally different. They did not see their mortar as static, but as dynamic and responsive, a living skin for a building that could adapt and mend itself across generations. This shifts the entire philosophy of construction from one of control and resistance to one of collaboration and resilience. What if our buildings could not just withstand the elements, but learn from them and grow stronger in response? The silent healing in those old walls suggests we once knew how to build a world that could take care of itself. This silent healing is powered by a patient partnership with the very air we breathe. At the heart of ancient mortar's longevity lies a process so gradual we can barely perceive it, a transformation that turns a potential weakness into its greatest source of enduring strength. We call this process carbonation. In the world of modern construction, carbonation is often viewed with concern. As carbon dioxide from the atmosphere slowly penetrates modern concrete, it can lower the material's alkalinity, which in turn can make the embedded steel rebar more vulnerable to corrosion. It is seen as a slow, inevitable decay. But in the lime-based mortars of the ancient world, this narrative flips completely. Here, carbonation is not a villain, it is the primary architect of long-term resilience. It is the mechanism that completes the material's journey back to stone. The story begins when the mortar is first placed between the bricks or stones. Within the wet paste are molecules of calcium hydroxide, the result of slaking quicklime with water. This substance is thirsty for a reunion. Over the years, even centuries, it begins a quiet dialogue with the atmosphere, absorbing carbon dioxide molecule by molecule. This slow chemical marriage transforms the soft, reactive calcium hydroxide into solid, crystalline calcium carbonate. This is the very same mineral that makes up limestone, marble, and seashells. The mortar is not just drying out, it is literally petrifying, turning back into a form of rock within the wall. This is a beautiful synergy with the environment. A greenhouse gas, carbon dioxide, is pulled from the air and locked away permanently, woven into the fabric of the building itself. The structure becomes a carbon sink, a geological process happening in human time. But the true genius of this system is in its pacing. The carbonation front moves inward from the surface at a rate of perhaps 1 millimeter per year. This glacial speed is perfectly matched to the life of a masonry structure. As a new building settles under its own weight, as the ground subtly shifts over decades, the mortar is not yet fully rigid. Its core remains slightly flexible, allowing it to accommodate these movements without catastrophic cracking. Then, as the years turn into centuries and the structure finds its equilibrium, the carbonation front steadily advances, converting more and more of the interior paste into dense, rock-like calcium carbonate. The strength of the wall increases in concert with its need for stability. It is a material that grows stronger as it ages, strengthening in response to the very passage of time that destroys lesser constructions. This stands in stark contrast to modern concrete, which achieves most of its strength within a month and then remains static or slowly degrades. The ancient recipe engineered a different kind of time. It created a material on nature's schedule, one that understood that true permanence is not a state achieved at completion, but a relationship maintained across the ages. The environmental cost of our modern strength is written in the sky itself. That gray powder, Portland cement, carries a hidden climate debt within every bag. To create it, limestone and clay must be baked in colossal kilns at a scorching 1,450 degrees Celsius, a temperature that rivals the surface of some volcanoes. This single industrial process is a voracious consumer of fossil fuels, and the chemical reaction itself releases vast amounts of trapped carbon dioxide. The staggering result is that cement production alone is responsible for roughly 8% of all human-caused carbon emissions worldwide. It is the invisible foundation of our built world, and also one of its heaviest atmospheric burdens. Now, compare this to the ancient lime cycle. Yes, it required energy, burning wood or charcoal to heat limestone in a kiln, but the temperatures needed were far lower, around 900 degrees Celsius, a significant difference in energy input. More importantly, the story does not end at the kiln's mouth. Modern cement, once set, is largely a closed book, its carbon released and done. Ancient lime mortar begins a long journey of reconciliation. As we just explored, that mortar slowly pulls carbon dioxide back from the atmosphere over decades and centuries, reabsorbing a portion of what was released during its creation. This turns a wall or a floor into a gentle carbon sink. When you then factor in the other half of the ancient recipe, the use of local, natural like volcanic ash or crushed brick, the environmental equation shifts even more dramatically. These materials required no high-temperature processing at all. They were simply gathered, ground, and mixed. A mortar made from locally slaked lime, and a nearby source of bypasses the global supply chains and the extreme heat of modern industry. Its total carbon footprint from cradle to grave can be a mere fraction of its modern counterpart. This is not about romanticizing the past, but about re-examining its efficiency. The ancient approach minimized embodied energy, the total sum of energy consumed by a material over its entire life cycle. They built with what the land provided, using chemistry rather than brute force heat to achieve strength. In an age defined by climate urgency, this forgotten wisdom points toward a more circular model of construction. What if the next generation of durable materials didn't demand such a fiery toll on our atmosphere, but instead engaged in a lifelong conversation with it? Locking carbon away in the very streets, we walk upon the quiet conversation within ancient walls, now speaks through the hum of machines. To truly understand what these forgotten recipes achieved, scientists have become detectives, subjecting fragments of 2,000-year-old mortar to the most advanced scrutiny our century can offer. This is not simple ingredient listing. It is a deep dive into the soul of the material, using tools like scanning electron microscopes that can see structures 1,000 times thinner than a human hair. An X-ray diffraction that reads the mineral fingerprint of a crystal. They are performing a kind of forensic archaeology on the nanoscale, reverse engineering the choices of a Roman mason or a Chinese builder to understand not just what they used, but how those ingredients dance together. The findings are nothing short of humbling. When researchers examine a sample of Roman seawater concrete, they do not find a chaotic, primitive paste. They map a meticulously organized landscape. They see the interlocking plates of crystals, grown over centuries, forming a dense, almost flawless matrix that resists crack propagation with a sophistication modern materials science strives to replicate. In the sticky rice mortar of the Ming Dynasty, they observe how the organic amylopectin chains directed the formation of exceptionally fine and interlocked calcite crystals, creating a composite tougher than the sum of its parts. These builders, without a single textbook on crystallography, were intuitively guiding matter to assemble itself into architectures of immense resilience at a scale invisible to the eye. They were nano-engineers long before the word existed. Their recipes were not random folklore. They were the product of generations of observed cause and effect, a slow, rigorous science of trial and error that yielded materials with performance profiles we are only now learning to measure. This laboratory rediscovery forces a profound shift in perspective. It moves these ancient techniques from the realm of mysterious legend into the domain of reproducible and potentially revolutionary material science. The past is not just showing us old ways of building. It is showing us a different, and perhaps wiser, way of thinking about how matter itself can be organized for longevity. This rediscovery is not merely academic. It is breathing new life into the very stones it once built. The most urgent and beautiful application of this ancient wisdom is unfolding in the quiet, careful world of historic conservation. For decades, well-intentioned restorers made a catastrophic mistake. When an old stone wall showed signs of wear, the instinct was to fix it with the strongest, most modern material available, Portland cement. The results were often devastating. That hard, impermeable cement mortar acted like a prison wall. It trapped moisture inside the historic masonry, preventing the stone from breathing as it was designed to do. With nowhere to go, that moisture would freeze in winter, expand and force the softer, original stone to flake and crumble in a process called spalling. The repair, meant to save the building, became an agent of accelerated decay, literally crushing the fabric it was meant to protect. It was a clash of material philosophies, a loud, rigid command shouted into a system built on quiet, flexible conversation. Today, leading conservators approach repair with a surgeon's reverence, guided by the principles we have just explored. Their first step is always forensic, analyzing a tiny sample of the original mortar to understand its exact composition, its porosity, even the size and shape of its sand grains. Then they become alchemists in their own right, mixing a custom, soft lime-based putty, often aged for months, and blending it with carefully selected sands and to match the historic recipe. This is known as a like-for-like repair. The goal is not to make the new mortar stronger than the old, but to make it a perfect match in strength, flexibility, and when this compatible mortar is gently tucked into a joint, it rejoins the building's natural system. It allows moisture to wick in and out harmoniously, it flexes with thermal movement, and it ensures that any future stress is distributed evenly across the masonry. The repair becomes invisible not just to the eye, but to the building's own physical logic. This philosophy acknowledges that a historic structure is a living document, its walls a record of centuries of interaction with the environment. To slap a modern cement patch over that is to tear a page from that story. To use a sympathetic, historically informed mortar is to add a new, respectful sentence, written in the same language as the original. It is an act of humility, admitting that the builders of the past often understood the long-term needs of their materials better than we did. In cathedrals across Europe and in ancient monuments worldwide, this quiet revolution is ensuring that these treasures do not become frozen museum pieces, but continue their ancient, breathing dialogue with time. Preserved not as relics, but as living legacies, the quiet art of conservation is a vital act of preservation, but a more ambitious question now drives material science forward. Can we not just repair the old ways, but build entirely new ones with the same ancient wisdom? This is the frontier of modern eco-cement, where laboratories are not merely copying recipes, but translating their core principles into a language for the future. One of the most promising paths takes its cue directly from the Roman love for volcanic ash. Today, we have a different kind of ash, a problematic byproduct of our own industrial age. Fly ash, the fine powder left from burning coal in power plants, and ground granulated blast furnace slag, a leftover from steel production. For decades, these were considered waste, destined for landfills. But to a materials scientist, they look remarkably familiar. They are rich in silica and alumina, the same reactive ingredients found in natural. By activating these industrial wastes with an alkaline solution, researchers create what are known as alkali-activated cements, or. The process is a direct echo of the ancient reaction, but supercharged and precisely controlled. The result is a binder that can match or even exceed the strength of Portland cement, while slashing its carbon footprint by as much as 80%. It turns a liability, industrial waste, into a high-performance asset, mimicking the Roman genius for using what the local environment provided, even if that environment is now a power plant. This is not nostalgia. It is a pragmatic reinvention, capturing the durable, low-energy chemistry of the past to solve a pressing modern dilemma. The goal is a concrete that doesn't just last, but does so without costing the earth. Meanwhile, another team of innovators is looking even further back, to the organic alchemy of sticky rice and egg whites. Their toolkit is microscopic, bacterial. Certain strains of bacteria, when provided with the right nutrients, naturally produce calcite, the same mineral that gives limestone its strength. Scientists are now harnessing this biological process to create biocement. Imagine injecting a solution containing these bacteria and a food source like calcium lactate into a crack in a modern concrete structure. As the bacteria metabolize, they precipitate a network of calcite crystals, seamlessly welding the fracture shut from the inside. This is autogenous healing, not as a passive chemical side effect of ancient lime, but as an actively managed biological repair system. It directly echoes the way organic additives in old mortars guided crystal growth, but with a new level of intentionality. We are learning to program life itself to maintain our infrastructure. These two strands of research, the and the Biocement, represent a profound shift in thinking. They move us away from the 20th century model of high heat and high emissions toward a model of low-energy chemistry and biological collaboration. They ask us to see waste as a resource and cracks as opportunities for regeneration. The ancient builders showed us that the most enduring materials are those that engage in a conversation with their world. Today, that conversation is expanding to include the very cycles of industry and the hidden capabilities of microorganisms. We are beginning to build not just with stone and sand, but with the legacy of our own byproducts and the quiet, creative force of life. Writing the next chapter in a story that began between the stones of a Roman harbor 2,000 years ago, the mortar that built Rome could not have built. This is the crucial, often overlooked truth. These forgotten recipes were not a single, monolithic secret to be cracked, but a living language of place. Their genius was not in standardization, but in radical localization. A master builder did not open a universal manual, he walked the land. He felt the grit of the local sand between his fingers, examined the color and texture of clay from a nearby riverbank, and sought out deposits of limestone with just the right purity. If the landscape offered the black, glassy sand of a volcanic field, that became his. If the region had deposits of a specific reactive clay, that was fired and crushed into his. In coastal areas, they might even incorporate crushed seashells, another source of calcium carbonate. The recipe was a direct reflection of the local geology, a collaboration with the very ground upon which the structure would stand. This necessity, born from the sheer difficulty of transporting heavy materials over long distances, forced an intimate, profound optimization. A mortar formulated for the salt spray and humidity of a Mediterranean port city like Ostia would have been disastrously wrong for the dry, freeze-thaw cycles of a mountain fortress in the Andes. The builders understood this intuitively. They engineered their adhesive to be in harmony with its specific environmental challenges, creating a bespoke solution for every unique location. This stands in stark opposition to our modern paradigm. Today, a skyscraper in Dubai, a bridge in Norway, and a dam in Brazil will likely all use the same globally sourced, standardized Portland cement, shipped across oceans in identical sacks. We have achieved incredible uniformity, but we have severed the vital link between a building and its biome. The ancient approach was inherently sustainable, not as a conscious ethical choice, but as a practical imperative. It minimized embodied energy long before the term existed, because the energy required was the labor to gather materials from within a few miles, not the fuel to ship them across continents. It created a circular economy on a local scale, where waste products like rice husk ash or crushed pottery found immediate, high-value use. This hyperlocal material science represents a deep form of ecological intelligence. It asked builders to listen to their environment, to understand its offerings and its aggressions, and to craft a response from within that same system. The lesson for our future may not be to rediscover one perfect Roman recipe, but to reclaim that fundamental mindset to ask, what does this place provide? And how can we build with it in a way that will last for centuries here? And only here this meticulous philosophy extended far beyond the quarry and into the mixing pit itself. The true secret was never just a list of ingredients scribbled on a parchment. It was a choreographed ritual of transformation, a sequence of steps as vital as the components themselves. Historical manuscripts and the oral traditions of master masons speak of this process with a reverence usually reserved for sacred rites. They dictated not only what to mix, but how, when, and for how long. A batch of mortar might be mixed not for minutes, but for hours, even days, by teams of laborers working in shifts. This was not mindless toil. It was a deliberate technique to achieve a state called a perfectly homogeneous, almost creamy paste where every particle of lime was fully suspended and hydrated. Imagine trying to make a truly lump-free batter by hand, where a single pocket of dry flour would ruin the entire cake. The ancient builder faced a similar problem on a monumental scale. And batch meant weak spots, points of failure where the chemical conversation could not properly begin. The prolonged mixing also incorporated air, which helped create a workable, plastic mortar that could be buttered onto stones with perfect adhesion. But the ritual did not end at the mixing trough. Timing was everything. Some traditions insisted mortar only be mixed and used during certain seasons, favoring the mild, damp days of spring or autumn over the drying heat of summer or the freezing cold of winter. This was an intuitive understanding of the cure, allowing the mortar to dry slowly and evenly, preventing the rapid moisture loss that leads to shrinkage cracks. The mortar itself often required a resting period after mixing. A final maturation in the trough before it was deemed ready for the trowel. This entire holistic procedure, from the slaking of the lime years prior to the final stroke of the mason's tool, was the complete recipe. The process was the guardian of the promise. It ensured that the potential locked within the volcanic ash or the sticky rice was fully awakened and perfectly blended, ready to begin its centuries-long dialogue with the stones. In a world without industrial mixers or chemical accelerants, this embodied knowledge, this patient ritual of hand and time, was the indispensable catalyst that turned raw earth into enduring legacy. The final trowel stroke on a modern skyscraper marks the end of a race against the clock. Construction schedules are measured in days and weeks, and the primary metric of success is a number printed on a lab report, the compressive strength achieved at 28 days. This figure is the gatekeeper, the proof that allows the next phase to begin, the scaffolding to come down, and the building to open. It is a system engineered for speed, for predictable financial returns, and for the relentless pace of contemporary development. But this very focus on short-term metrics creates a built environment with a kind of temporal myopia. We are optimizing for the moment the certificate of occupancy is granted, not for the century the building will hopefully stand. The material is pushed to perform quickly, to reach a high plateau of strength as fast as possible, and then its chemical life is largely over. It enters a long, slow decline, its brittle nature waiting for the first stress it cannot withstand. The ancient builder operated on an entirely different calendar, one not of quarters, but of queens and emperors, of dynasties and faiths that were meant to outlast any single lifetime. When a master mason placed the keystone in a Gothic vault, he was not thinking about 28 days. He was thinking about the judgment day his cathedral depicted, a timescale that stretched into eternity. His mortar was engineered for that timeline. It was designed to gain strength not in a month, but over decades, to remain slightly plastic and adaptable as the massive stone skeleton settled into its final pose over years. Its performance peak was not a date on a chart, but a slow, rising curve that might not reach its zenith for 100 years. This is a fundamental philosophical schism in how we relate to our own creations. One culture builds for the investor's timeline, the other for the lineage of a civilization. We see our structures as products with a depreciating value and a planned service life. They saw theirs as legacies, as permanent additions to the world that would carry memory and identity forward. This cultural mindset of intergenerational investment shaped every aspect of material choice. Why worry if the lime putty needs to age for 10 years in a pit, if the wall it will hold is intended to stand for 1,000? Why not spend a week mixing a batch to perfect consistency, if that batch will silently uphold a roof for 50 generations? The cost, the labor, the patience, all of it was amortized across centuries. In our modern calculus of immediate efficiency, that kind of patience is untenable, but it raises a disquieting question about what we are actually optimizing for. Are we building a world that is merely efficient to construct, or are we building one that is wise enough to endure? That patient, intergenerational mindset was not just philosophical. It was physically etched into the very fabric of the material. To understand why, we must shrink our perspective down, far down, to a realm the ancient builders could never see but somehow mastered. The ultimate secret of their mortar's resilience is written in a hidden landscape, a world within a grain of sand. Under the powerful gaze of a modern electron microscope, the true architectural genius of these old recipes is revealed. It is not a story of uniform perfection, but of beautiful, resilient complexity. The microstructure of a superior ancient mortar is a bustling, heterogeneous metropolis. You see the remnants of the carefully aged lime putty, now transformed into a dense forest of interlocking calcium carbonate crystals. Woven through this forest are the particles, like rugged islands, each one surrounded by a halo of even finer, tougher crystals that grew from the slow chemical reaction between the lime and the silica. Crucially, you also see a delicate, even distribution of tiny air voids, like a network of microscopic ball bearings. These were not flaws. They were often intentionally introduced by the prolonged mixing or by the foaming action of organic additives. This intricate, varied nanoscale architecture is the source of its legendary toughness. Toughness is different from hardness. Hardness is about resisting a scratch or a dent. Toughness is about absorbing energy, about bending rather than breaking. Think of a flexible hardwood floor versus a ceramic tile. Drop a heavy object on both. The tile, being hard but brittle, shatters. The wood, being tough, dense but does not fail catastrophically. The ancient mortar's microstructure mimics the wood. Those interlocking crystals and islands create countless, meandering pathways for a crack to travel. When a stress wave from an earthquake or settling ground tries to propagate a fracture, it is constantly forced to change direction, to navigate around a hard particle, or dissipate its energy into an air void. The crack slows down, it tires, and it stops. It is a material designed to blunt the advance of its own destruction. Now, compare this to the microstructure of a typical modern Portland cement paste. Under the same microscope, it can appear more homogeneous, more uniform. Its crystals are often smaller and more densely packed, which gives it that impressive, early compressive strength. But this uniformity is also a weakness. When a crack begins in this environment, it finds a straight, unimpeded highway. There are fewer obstacles to divert it, fewer energy-absorbing features to slow it down. The crack propagates quickly and cleanly, leading to the sudden, brittle failures we associate with concrete cancer or spalling. The ancient builders, without a single lens or textbook on fracture mechanics, empirically developed mixes that optimized this invisible architecture for resilience. They used time, specific ingredients, and meticulous process to build a nanoscale maze within their walls, a maze that any force of decay would get lost in. They were not just stacking stones, they were engineering chaos at the molecular level, a chaos that created the most profound order of all, endurance. This nanoscale maze within ancient mortar was not just a defense against earthquakes, but a blueprint for weathering the coming storm. As our world warms and weather patterns grow more extreme, the resilience coded into these old materials offers not just historical curiosity, but a critical survival manual. Our modern infrastructure is facing unprecedented assaults, from rising sea levels and intensifying floods to more frequent and severe freeze-thaw cycles. The very brittleness and impermeability that shortens it is becoming a catastrophic liability. Here, the ancient philosophy of building with the environment, not against it, provides a powerful alternative path. One of the most vital lessons lies in a property modern engineers often try to eliminate: porosity. Ancient mortars were designed to be highly permeable to breathe. This might sound like a weakness, letting water in. But in a world of increasing deluges and temperature swings, it is a profound strength. When rainwater soaks into a wall made with breathable lime mortar, it is not trapped. The material's open structure allows that moisture to slowly wick back to the surface and evaporate harmlessly. Now, consider the destructive power of a freeze-thaw cycle in a modern concrete sidewalk. Water seeps into a micro-crack, freezes, expands by 9% and forces the crack wider. Repeat this process dozens of times a winter and the sidewalk turns to rubble. In a breathable ancient wall, the water is not held in a confined space long enough for this destructive expansion to occur. The wall manages moisture like a living system, taking it in and releasing it, maintaining a healthy equilibrium that prevents the internal pressures that cause modern materials to explode from within. This inherent ability to handle water without damage is an impassive climate adaptation, a built-in resilience we desperately need to replicate. Beyond the physical management of water, these ancient recipes also show remarkable chemical fortitude against specific threats amplified by climate change. Take sulfate attack, a silent killer of modern concrete. Sulfates, naturally present in many soils and in high concentration in seawater, slowly infiltrate modern concrete and react with its compounds. This reaction forms expansive crystals that generate immense internal pressure, crumbling the material from the inside out. As sea levels rise and storm surges push further inland, this form of decay will accelerate. Yet Roman seawater concrete, submerged for, shows minimal sulfate damage. Its chemical formulation, particularly the formation of stable minerals like aluminous, is inherently less reactive to sulfate ions. The material was essentially vaccinated against its environment. This is not a lucky accident, but a result of tailoring the chemistry to the known challenge. For coastal cities building new or fortifying foundations against intrusion, this ancient example is a direct challenge to our material choices. Are we using a chemistry that fights the sea, or one that finds a stable, durable truce with it? The imperative now is to translate these passive, ancient strengths into active, modern innovation. The goal is not to abandon concrete, but to reinvent it using this old wisdom as a guide. Imagine a new generation of infrastructure concrete designed for coastal megacities. Inspired by Roman harbors, it would use industrial like fly ash to create a chemistry that thrives in, forming self-strengthening minerals over time. Its microstructure would be engineered for controlled permeability, allowing it to breathe and manage moisture without sacrificing strength. For regions facing more extreme temperature swings, we could design concretes with internal micro-voids, mimicking the air-entraining effect of organic additives. Giving water room to expand when it freezes without causing damage. This is biomimicry at the material level, learning from structures that have passed the ultimate stress test of time. The research is already moving in this direction, with scientists developing ductile, self-healing concretes and low carbon. But the ancient examples provide something crucial, a proven long-term performance record. They are the control group in a 2,000-year-long experiment, showing us what truly works. In a warming world where rebuilding after every major storm is neither economically nor ecologically sustainable, the most forward-thinking thing we can do may be to look back. To learn from the mortars that turned environmental challenges into sources of enduring strength. The question is no longer if our materials can be strong tomorrow, but if they can be wise enough to remain strong a century from now, in a climate we are only beginning to understand. The Pantheon was not built by aliens. Its dome is not held aloft by a mythical, vanished super cement. These persistent legends, while entertaining, do something subtle and damaging. They rob the ancient builders of their true genius, replacing their hard-won mastery with an X of fantasy. The reality is far more compelling because it is human. The longevity we marvel at was not a happy accident or a gift from the stars. It was the result of a sophisticated, systems-based approach to construction, a holistic philosophy where every choice, from the quarry to the final trowel stroke, was interconnected. This was a science built on deep, generational observation. A master mason did not need a modern laboratory to understand that mortar made with ash from a certain hill resisted seawater better. He had the laboratory of time itself, observing which buildings stood and which fell over the course of his own life and the stories of his grandfather. This empirical method, repeated across continents and cultures, yielded a profound material intelligence. The secret was never a single, magical component. It was the entire system. It was the choice of a locally sourced that reacted perfectly with the locally slaked lime. It was the architectural design, like the thick, compressive mass of a Roman arch, that worked in harmony with the mortar's properties. It was the patient processing, the years of aging and days of mixing, that prepared the material for its long chemical conversation. Demystifying these recipes does not strip away their wonder, it redirects our awe to its proper place. The wonder is not in a lost, unrepeatable magic, but in a repeatable, deeply intelligent process. It shows us that our ancestors were not primitive, but were expert nano-engineers and systems thinkers who manipulated matter with a finesse we are only now relearning. This shift in perspective is crucial. Viewing these structures as products of alien technology or lost super science makes their lessons irrelevant to us. It places their achievement outside of human capability. But understanding them as the pinnacle of observation-based craft and localized material science does the opposite. It provides a practical, inspiring blueprint. It tells us that durability is not a mystery, but a discipline. It is a discipline of using what you have, of understanding the environment you are building within, of prioritizing long-term performance over short-term speed, and of seeing a building not as a collection of separate parts, but as a single, integrated organism. The true legacy of the Roman concrete mixer or the Ming Dynasty mortar crew is not a list of ingredients, but a way of thinking. It is a testament to human ingenuity that solved for permanence, and in doing so, left behind a silent, stone-coated manual for how we might build a world meant to last. This long-term perspective reveals a profound economic paradox. The initial invoice for a Roman harbor or a Gothic cathedral would have been staggering, a monumental investment of labor, materials, and time. By our modern, just-in-time accounting, ancient mortar was wildly expensive. Consider the man-years spent slaking lime in pits for a decade, or the teams mixing a single batch for days on end. Compare that to the efficiency of a modern cement truck, rolling up to a site and pouring a foundation in hours. On a spreadsheet measuring upfront cost and speed, modern concrete wins every single time. But that spreadsheet has a critical flaw. It only calculates the first column, the construction cost. It ignores every column that comes after, stretching across the centuries. This is where the entire economic model flips. Let us project the ledger out over 500 years. On one side, you have a structure built with that patient, ancient mortar. Its maintenance costs over 5 centuries are virtually zero. No major repairs, no invasive restorations, just the quiet, continuous operation of its self-healing chemistry. The initial high investment is amortized across those 500 years of flawless service, making its annual cost astonishingly low. Now, look at the other side of the ledger. A modern concrete structure, even a well-built one, has a typical design life of perhaps 50 to 100 years. Over that same 500-year period, it would likely require multiple major refurbishments, perhaps even a complete rebuild. Each of those events carries a massive financial cost, not to mention the disruption and the environmental toll of demolition and new construction. Suddenly, the material that seemed so cheap at the outset becomes the far more expensive option over the long arc of time. The ancient builders were not just masters of materials, they were masters of a different kind of economics, one that valued intergenerational return on investment. They built for the lineage, not just the ledger of a single fiscal year. Our contemporary accounting models, focused on quarterly reports and immediate capital outlay, are structurally blind to this kind of value. We have no widespread mechanism for calculating the full cost, the true cost of ownership that includes centuries of maintenance, energy use, and eventual disposal. This creates a perverse incentive. It is always cheaper, in the short-term view that dominates our markets, to choose the material with the lower initial price tag. Even if it dooms future generations to pay a much higher price in repairs and replacement. We are, in essence, borrowing from the future to make our present construction budgets look good, passing a hidden debt of decay and waste to our children and. The ancient approach demanded more from the generation that built, so that 100 generations that followed could inherit an asset, not a liability. This is not merely a historical curiosity. It is a direct challenge to how we value our world today. What if our buildings came with a 500-year warranty and their price reflected that promise? The quiet stones of an old aqueduct ask us to reconsider what true economy really means. Is it the cheapest way to build something now, or the wisest way to build something forever? That long-term economic vision is now finding new champions with trowels in hand. A quiet revolution is taking shape not on vast construction sites, but in workshops and field courses, where architects, engineers, and masons are getting their hands dirty with the very materials they once studied only in history books. This is an educational revival, a conscious effort to reclaim the tactile wisdom of traditional lime mortars before it fades from living memory. Across the world, you can now find courses where professionals and enthusiasts learn the almost forgotten arts of hot lime mixing, the careful slaking of quicklime, and how to identify local soils and ashes with potential. They are not just reading about these processes, they are feeling the heat of the reaction, smelling the sharp scent of wet lime, and learning the subtle difference in texture between a well-aged putty and a fresh one. This movement is not a wholesale rejection of modern concrete or steel. That would be impractical. Instead, it is about intellectual and practical expansion. The goal is to give today's builders a richer, more nuanced toolkit. By truly understanding the principles behind these ancient materials, why they breathe, how they flex, the way they interact with historic stone, professionals can make far more informed choices. They gain the discernment to know when a modern, high-strength adhesive is the right tool for a new skyscraper's foundation, and when a soft, vapor-permeable lime mortar is the only responsible choice for repairing a 200-year-old brick wall. This knowledge empowers a hybrid approach, blending the best of the old and the new. For new construction in sensitive environments, like building a home with traditional materials, it allows for walls that manage moisture intelligently and age with grace. In the critical field of historic restoration, it is nothing short of essential. It transforms a conservator from someone who applies a generic product to a guardian who speaks the material language of the original structure, ensuring repairs protect rather than entomb. This revival turns historical curiosity into a practical, sustainable skill, ensuring the next generation of builders doesn't just look at ancient walls with wonder, but knows how to care for them. And perhaps how to build new ones with the same enduring wisdom. A fragment of mortar is no longer just a piece of old glue. In the hands of a modern biologist, it becomes a record of an ancient ecosystem. To a geologist, it reads like the slow story of a forming rock. Chemists see within it a symphony of reactions playing out over centuries. The quest to understand these forgotten recipes has sparked a remarkable convergence of sciences, each bringing a unique lens to decipher a single, profound truth. The ancient builders were practicing a form of integrated science long before our modern disciplines ever existed. They operated at the intersection of fields they could never have named, but whose principles they mastered through observation and craft. A biologist might take a sample from a Ming Dynasty wall bound with sticky rice mortar. Their focus is not just on the starch, but on the invisible world it influenced. They study how that organic matrix created a microenvironment hostile to destructive microbes, yet potentially hospitable to benign, mineral-forming bacteria. The mortar becomes a managed biome, a crafted landscape at the microscopic scale where chemistry and biology collaborate to resist decay. This perspective reveals that adding egg white or blood was not merely a chemical act, but an ecological one. The builders were intuitively manipulating the tiny life on their walls, guiding it toward stability rather than ruin. Meanwhile, a geologist approaches the same sample not as a building material, but as an artificial sedimentary rock. They apply the same tools used to date limestone layers or understand lava flows. They look for diagenesis, the slow post-depositional changes that turn loose sediment into solid stone. In a Roman concrete core, they trace the gradual, inward march of the carbonation front like a geological event. They identify the formation of rare minerals like aluminous as a metamorphic process, a transformation under the mild, persistent pressure of seawater over. To a geologist, the harbor at Caesarea is not a ruin. It is a young, still-forming geological deposit, its crystallization process ongoing. This view frames the builders as accelerated geologists, speeding up natural rock-forming processes with heat and mixture to achieve in decades what nature might take to do. Then the chemist enters the conversation, armed with equations and models. Their challenge is to quantify the patience. They study the reaction kinetics, the precise speeds at which lime and combine over years. They map how the presence of organic molecules alters the nucleation sites for crystals, guiding their growth into tougher, more interlocked networks. For them, the recipe is a complex chemical formula with variables for time, temperature, and ingredient purity. They seek to replicate not just the composition, but the timeline to create a modern equivalent that gains strength not in weeks, but in a slow, steady crescendo. This interdisciplinary dialogue is crucial because no single field holds the complete cipher. The biologist alone cannot explain the seismic resilience coded into the mortar's microstructure. The geologist cannot fully account for the role of casein proteins. The chemist's models need the real-world, long-term data that the geologist's rock analysis provides. Together, they are performing a kind of scientific triangulation, fixing the true position of this ancient knowledge from multiple angles. What emerges is a humbling portrait of holistic understanding. The master mason who a certain volcanic ash aged his lime for a decade and demanded the mortar be mixed for 3 days was balancing chemistry, geology, and practical biology in a single elegant act of construction. He was thinking in systems, not in isolated components. Our modern specialization, while powerful, can sometimes blind us to these deep connections. We have experts in concrete, experts in steel, experts in insulation. The ancient builder had to be an expert in the entire, integrated behavior of his local earth, fire, water, and air. This collaborative scientific decoding does more than satisfy historical curiosity. It provides a new language for innovation, a shared vocabulary that allows a materials scientist to talk to a microbiologist about designing the next generation of self-healing concrete. It proves that the most enduring solutions often lie not in a single, narrow discipline, but in the fertile ground where they all meet, just as the ancient artisans seemed to know all along. The quiet chemistry within a sample of ancient mortar can now be simulated inside a supercomputer. Beyond the microscope and the chemical assay, a new kind of laboratory exists in the digital realm, where researchers are using advanced computational models to stress test these forgotten recipes in ways that would take centuries in the real world. This is the frontier of finite element analysis, a powerful simulation tool that breaks down a complex structure, like a Roman arch or a Gothic flying buttress, into millions of tiny, interconnected digital cubes. Each of these virtual cubes can be assigned the precise material properties discovered in the lab, the density, the elasticity, the porosity of a specific historic mortar. Then the simulation begins. The digital model can apply the relentless force of gravity over 1,000 years, simulate the expansion and contraction of countless freeze-thaw cycles, or recreate the violent shaking of a major earthquake. Researchers can watch, in accelerated time, how stresses flow through the virtual masonry, identifying exactly where a weaker or more brittle modern mortar would develop catastrophic cracks, and where the flexible, self-healing ancient recipe would simply absorb and redistribute the energy. This is not guesswork, it is a quantitative revelation. It translates the poetic idea of resilience into hard numbers, graphs, and stress maps. For the first time, we can put a data-driven value on the wisdom of the ancients, calculating exactly how much more seismic load their bespoke mortar could handle compared to a standard modern mix. The simulation reveals the hidden logic in the design, showing how the choice of glue was as critical to the building's survival as the shape of the arch itself. It proves that their longevity was not mystical, but mechanically inevitable given their material choices. This digital testing ground allows us to run experiments that history never performed, answering questions we could only previously ponder. What if the builders of the Colosseum had used a slightly different volcanic ash? What if the mortar in a fragile medieval tower was replaced with a modern cement during a past restoration? The simulation can show the likely outcome, providing a stark visual and mathematical cautionary tale. Furthermore, this technology enables the creation of digital twins, exact virtual replicas of existing ancient structures. Scientists can instrument a real-world monument with sensors to monitor temperature, humidity, and minute movements, then feed that live data into its digital twin. They can then use the model to forecast future decay under changing climate conditions, or to test the impact of different conservation mortars before a single trowel touches the historic stone. This virtual sandbox becomes an invaluable tool for preservation, allowing conservators to preview the long-term consequences of their interventions across decades in a matter of hours. Ultimately, this computational power is guiding the most practical goal of all, the creation of new hybrid materials. By understanding exactly which property of the ancient mortar, its controlled porosity, its specific crystalline structure, its chemical reactivity, contributes most to its performance. Material scientists can design targeted modern. They can ask the computer to optimize a new recipe for maximum crack resistance or for ideal thermal buffering in a specific climate. The digital models serve as a bridge between the empirical genius of the past and the precision engineering of the future, turning the silent endurance of old stones into a blueprint for the resilient infrastructure of tomorrow. The specific formula in a wall can tell you where you are in the world. This is the deeper truth that moves beyond chemistry and into the realm of identity. When a mason in medieval Burgundy used a pink lime mortar mixed with crushed local tile, he was not just solving a structural problem. He was embedding the very geology of his homeland into the cathedral rising above the town. The recipe was a signature, a declaration of place. It said, "We build with what this land gives us, and in doing so, we become part of its enduring story." Across the globe, this pattern repeats, creating a rich tapestry of localized knowledge. The sticky rice mortar of southern China speaks of a wet, rice-cultivating culture that learned to weave its staple crop into its monuments. The volcanic ash mortars of the Andes tell of communities living in the shadow of powerful mountains, harnessing their fiery residue for stability. The of Italy, made from the rubble of older buildings, whispers of a culture that saw value and continuity in its own history, literally recycling the past to build the future. Each mix is a unique fingerprint, born from a specific intersection of available resources, climate challenges, and cultural practices. This accumulated wisdom, passed from master to apprentice over centuries, represents what we now call intangible cultural heritage. It is not just the physical cathedral or temple that matters, but the living knowledge of how to build it, the unspoken understanding of proportions, the feel of the right consistency in the mix. The seasonal timing of the work. This knowledge is the true legacy, a collective intelligence forged through generations of trial and error, success and collapse. To lose these recipes is not merely to forget a technical detail. It is to sever a vital thread of cultural memory. When we replace a historic lime mortar with a uniform cement patch, we are not just applying a different glue. We are erasing a local language of construction and imposing a global, generic one. We are silencing the specific conversation that building was having with its environment and its people. Preserving and understanding these ancient formulas, therefore, becomes an act of preserving diversity itself. It is a way of honoring the countless human journeys of adaptation and ingenuity. By studying why a certain mix worked in a certain place, we learn more than material science. We learn how people understood their world, how they related to their local landscape, and how they expressed their identity through the very substance that held their communities together. The mortar joint becomes a tiny, profound archive, holding within its gritty matrix the story of a culture's relationship with stone, earth, and time. To read that story is to connect with a fundamental human impulse, to create a mark of belonging meant to outlast a single lifetime, a whisper from the past about how to build a meaningful place in the world. The walls of tomorrow may not just stand, they may think. This is the audacious promise emerging from laboratories where ancient principles are merging with 21st-century technology. The ultimate legacy of those forgotten mortar recipes is not a historical footnote, but a radical roadmap, inspiring a new frontier of programmable and living construction materials. Scientists are now looking beyond merely mimicking the past, aiming to engineer a future where our infrastructure possesses a kind of embedded intelligence. Imagine a concrete that doesn't just passively wait for a crack to form, but actively senses the damage and responds. Researchers are developing systems with tiny, fluid-filled microcapsules or delicate glass tubes embedded within the concrete matrix. When a crack propagates through the material, it ruptures these vessels, releasing their contents. Inside could be a healing agent like a water-resistant polymer, or even a solution containing the very lime and silica precursors that fueled ancient reactions. The crack becomes its own repair kit, automatically sealed from within. This is not science fiction. It is a direct, high-tech echo of the self-healing mechanisms we observed in Roman seawater concrete, where moisture and residual lime slowly knitted fractures back together over decades. The modern version simply accelerates and automates that ancient, patient conversation. This vision extends further into the realm of biology itself. Another line of research takes its inspiration from the organic alchemy of sticky rice and egg whites, but with a precise, programmable twist. Scientists are experimenting with embedding specific strains of bacteria, along with a nutrient source, directly into the concrete mix. These bacteria lie dormant, preserved in microscopic spores. But when a crack forms and allows water and air to penetrate, the spores awaken. The bacteria begin to metabolize their stored nutrients, and as a byproduct of their life process, they precipitate calcite, the same mineral that makes up limestone. They literally excrete a natural cement, filling the crack from the inside out with a robust, biological stone. This process, known as microbial-induced calcite precipitation, is a brilliant form of biomimicry. It harnesses a natural, life-based repair system, creating a material that can regenerate itself much like living tissue heals a wound. It is the ancient wisdom of using organic matter to guide mineral growth, now upgraded with the precision of modern microbiology. The goal is a built environment that maintains itself, reducing the colossal economic and environmental costs of constant human intervention. The ambition grows even more profound toward the concept of a truly living building skin. Researchers envision facades and structural components that can adapt dynamically to their environment, much like the ancient mortars that were engineered for specific local climates. Imagine a wall surface embedded with materials that change their porosity in response to humidity, opening microscopic vents to release moisture during a rainstorm and closing them in dry heat to retain thermal mass. Think of concrete that contains phase change materials, substances that absorb heat as they melt and release it as they solidify. Acting as a passive thermal battery to regulate a building's interior temperature without any electrical input. These are not static barriers, but responsive interfaces, constantly negotiating with sunlight, air, and water to maintain optimal conditions inside. This transforms a building from an inert object into a participatory system, an organism engaged in a constant, energy-efficient dialogue with its surroundings. The ancient builders sought harmony with their environment through material choice. We are now learning to engineer that harmony directly into the material's behavior. The ancient goal of creating dynamic, responsive materials is becoming the defining challenge of modern smart infrastructure. We are moving from construction as assembly to construction as cultivation, from building things to growing systems. The quiet intelligence coded into a 2,000-year-old mortar joint, its ability to breathe, to flex, to heal, is the prototype for this new paradigm. It proves that longevity is not about resisting change, but about embracing it with a built-in capacity for adaptation. The future may see bridges that report their own stress levels, foundations that strengthen themselves in earthquake-prone zones, and cityscapes that manage stormwater and urban heat through their very skin. This is not a rejection of the past, but its fullest realization. By finally understanding the deep material conversations our ancestors initiated, we are now learning the grammar to write the next chapter ourselves, creating a world where our buildings are not just shelters, but wise and enduring partners in the life of a changing planet. Yet simply copying an ancient formula into a modern cement plant is a recipe for failure. The challenge we face is not one of ingredients, but of translation. Think of it like this: you cannot take a handwritten family recipe for a perfect sourdough, scribbled for a wood-fired hearth, and expect it to work flawlessly in a high-speed commercial bakery, using different flour and electric ovens. The core wisdom of fermentation and patience is still true, but the entire process must be re-engineered for a new context. This is the precise, complex task facing material scientists today. The Roman Pozzolana was a specific volcanic ash with a unique mineral fingerprint. The limestone they used was of a particular purity. Even the sand they mixed in, the aggregate, had a shape and texture that played a role in the final matrix. We cannot simply dig up the same materials in the same quantities to rebuild global infrastructure. Our modern quarries, our industrial sands, even our volcanic ashes are different. More fundamentally, the scale and speed of modern construction are alien to the ancient world. We pour foundations for skyscrapers in continuous, truck-by-truck operations that last for days, not the slow, lift-by-lift assembly of a Roman wall. Our materials must perform predictably in this fast-paced, mechanized environment. So the real work is not in the copying, but in the decoding. Researchers are not trying to find the lost Roman recipe book. They are using those ancient structures as a 2,000-year-long performance report. They ask, what underlying principle made this work so well? Was it the specific ratio of lime to reactive silica? Was it the way the curing process created a certain microscopic foam-like structure that absorbed stress? Was it the chemical pathway that allowed the material to remain slightly flexible for decades? Once they isolate these principles, the next step is the translation. Can we achieve that same beneficial microstructure using fly ash from a coal plant? Can we design a chemical admixture that encourages slow, continued strength gain in a concrete that also sets fast enough for a bridge deck? Can we program it to perform that same self-healing trick, but initiate it with a design trigger rather than waiting for random environmental moisture? This translational research is where the ancient and the modern truly meet. It requires a deep humility, an admission that our ancestors solved for variables we often ignore, like time itself. But it also requires bold innovation, using tools like computational chemistry and nano-engineering to rebuild those ancient virtues in a form our world can use. The goal is not to pour Roman concrete again. The goal is to create a new material that carries the same soul, a soul of resilience, dialogue, and timeless patience, but born from the realities and the responsibilities of our own age. This is the quiet, meticulous work that could redefine what it means to build for the future, by first understanding what it truly meant to build for eternity. A patent filed last year claims a revolutionary self-healing concrete. Its secret ingredient is a synthetic version of a compound first identified in Roman harbor walls. This moment captures a profound and delicate tension. As laboratories transform forgotten recipes into tomorrow's commercial products, a quiet ethical question emerges from the dust of history. Who truly owns this ancient knowledge? When a 2,000-year-old material principle becomes the foundation of a 21st-century billion-dollar industry, where does credit belong, and who deserves to benefit? This is not merely a legal debate about intellectual property. It is a deeper conversation about respect, legacy, and how we honor the silent architects of the past. The mortar that held the Maya's observatories together, or gave strength to Roman aqueducts, was not developed in a corporate research and development lab. It was the hard-won, collective intelligence of entire cultures, refined over generations through observation, failure, and triumph. That knowledge was a cultural asset, as integral to their identity as their language or art. To extract the chemical formula while disregarding its human source feels, to many, like a new form of taking. Imagine a pharmaceutical company isolating the active compound from a traditional healing plant used by an indigenous community for centuries, patenting it, and selling it back to the world without any acknowledgement or return to the people who preserved that wisdom. The parallel in material science is striking and equally fraught. The ethical challenge is to navigate a path between open scientific progress and just recognition. One perspective argues that knowledge this old belongs to the common heritage of humanity. These structures have stood for their secrets openly available for anyone to study. Decoding them benefits everyone, leading to more durable, sustainable infrastructure for all. Patenting a specific modern application of a broad ancient principle, they argue, simply protects the investment in the modern translation and manufacturing process, not the idea itself. Yet another, increasingly vital perspective emphasizes the rights of descendant communities and the concept of traditional knowledge protection. For them, it is about sovereignty and respect. If a company profits from a modern concrete inspired by, say, the unique hydraulic lime formulations of the Khmer Empire, should not some portion of that benefit support cultural preservation or education in Cambodia? Should not the innovation be acknowledged as a collaboration across time, rather than a purely modern invention? This is the emerging framework of benefit sharing, where commercial entities that utilize traditional knowledge engage in agreements to return a share of profits or provide other support to the originating communities. It is a way of closing the circle, ensuring that the legacy of the past nourishes the future of those who are its custodians. Navigating this landscape requires a new kind of sensitivity from scientists and corporations. It begins with attribution, openly and proudly stating the historical inspiration. It involves engaging with historians and, where possible, cultural representatives, not just engineers. The goal is to move from extraction to partnership, even when the original innovators are centuries gone. The most ethical path forward may be to see ourselves not as discoverers of lost secrets, but as students and stewards of an ongoing human project. The true value of these ancient recipes is not just in their chemical composition, but in the worldview they represent, one of harmony with local materials and intergenerational responsibility. To commercialize the chemistry while ignoring that deeper wisdom would be to repeat the old mistake of valuing only the part we can easily measure. The mortar between the stones asks us to build not just stronger materials, but more equitable frameworks for innovation, where the past is recognized as a co-author in the story of our future. The story of mortar is not a single thread, but a woven tapestry spanning continents and centuries. Every great civilization that sought to build for the ages faced the same fundamental challenge, and each arrived at its own brilliant, localized solution. In ancient Egypt, the builders of the pyramids used a lime-based plaster, often mixed with gypsum, to smooth the colossal limestone blocks and seal the tombs within. This was a mortar for eternity, designed to protect the sacred resting places of pharaohs from the ravages of time and the elements. Far to the east, in the fertile crescent of Mesopotamia, masons turned to a different resource entirely: bitumen. This naturally occurring tar, seeping from the ground, was heated and mixed with sand and crushed reeds to create a waterproof mortar ideal for the damp conditions of the Tigris and Euphrates River valleys. It held together the bricks of ziggurats and palaces, a sticky, black glue against the constant threat of water. Meanwhile, in the sophisticated cities of the Indus Valley, engineers developed early forms of hydraulic cement. They used a burnt limestone mixture that could set even in the humid climate, creating durable floors and tanks that managed water with astonishing precision. And high in the Andes, the Inca mastered the art of dry stone fitting to a degree that often makes mortar seem unnecessary. Yet for their most important structures, they employed a lime mortar made from seashells. Carrying the chemistry of the distant ocean up into the mountains to bond their majestic, earthquake-resistant walls. This is not a linear history of improvement, but a chorus of simultaneous innovation. From the deserts of Egypt to the mountains of Peru, from the river plains of Mesopotamia to the urban grids of the Indus, each culture looked to its immediate environment and asked, "What here can make our buildings last?" They did not have a global network to share blueprints, yet they converged on remarkably similar principles. They universally sought out local materials, whether it was Nile gypsum, Mesopotamian bitumen, or Andean limestone. They each experimented with reactive additives, from crushed bricks to specific clays, intuitively understanding that a simple paste could be transformed into something far stronger. And above all, they shared an empirical drive toward permanence, a deep cultural imperative to create legacies in stone. This global tapestry reveals something profound about our shared human journey. The desire to build something that outlives us, to leave a mark of meaning and memory upon the earth, is a universal impulse. The specific recipes differed wildly, but the underlying goal was the same: to converse with time and win. Each mortar mix was a love letter to the future, written in the silent, enduring language of chemistry and craft. The final, vital ingredient was not in the mix itself, but in the hands that placed it. Every batch of ancient mortar was a performance, and the mason was its conductor. His skill determined whether the chemical potential locked within the lime and ash would be fully realized or tragically wasted. This was knowledge written in muscle memory, not in manuals. A master understood the feel of a perfect putty, a texture he described as fatty or buttery, clinging to his trowel without being sticky. He knew the exact amount of water to add on a humid morning versus a dry afternoon, a calibration made by eye and touch. When he loaded his hawk and brought the mortar to the wall, his movements were deliberate. He would butter the stone thoroughly, ensuring every microscopic pore on its rough surface was filled, before setting the next block with a firm, settling tap. Then came the tooling, the careful shaping of the joint with a specialized iron. This was not for aesthetics alone, though the graceful concave or beaded profiles are beautiful. This compression of the surface skin of the mortar increased its density right at the point of exposure, creating a harder, more weather-resistant seal that shed water like a duck's back. A poorly tooled joint, left porous and rough, would invite water in and begin the slow process of frost damage from day one. The master's touch was the quality control system. He could feel a batch that was too sandy, hear the hollow sound of a poorly bonded stone when tapped with his hammer's handle. This deep, tactile literacy was cultivated over a lifetime, passed from experienced hands to calloused young ones on scaffolding high above the streets. It was a continuous, real-time dialogue between the craftsman and his material, a feedback loop of pressure, sound, and texture that no sensor could replicate. In our world of automated batching plants and laser-guided masonry saws, we have engineered the human variable out of the process for the sake of perfect uniformity. But in doing so, we may have lost the final safeguard, the discerning eye and sensitive hand that could catch a subtle flaw in the mix, adjust the technique for the day's weather, and ensure that every single joint was not just filled, but forged. The ancient wall endures not just because of what was in the mortar, but because of the wisdom in the hands that put it there. These whispers from the stones are not echoes of a lost golden age, but a clear and urgent conversation with our present. The forgotten mortar recipes dismantle the myth that longevity requires some unrepeatable magic. They were instead the brilliant application of deep observation and patient craft, in collaborating with nature rather than commanding it. Their central lesson is a radical shift in perspective. Durability is not a static property you pour into a mold, but a dynamic dialogue. It is the ongoing conversation between a breathable lime paste and the humid air, between a volcanic ash and the salt of the sea, between the slow growth of crystals and the settling of the earth. This dialogue acknowledges that a building is not an isolated object, but a participant in its environment, and its strength is not a peak reached at completion, but a capacity that can deepen with the passing years. This understanding reframes our very definition of sustainability. Today, we often measure it in recycled content or energy efficiency at the moment of construction. The ancient builders measured it in centuries of silent, uninterrupted service. Their sustainability was not a checkbox, but a legacy, a material philosophy that asked what the local land could provide and how it could be shaped to shelter generations yet unborn. As we confront the monumental task of building a resilient future against rising seas and intensifying storms, these time-tested principles offer more than historical intrigue. They provide a vital blueprint. They show us that the most resilient materials are those designed to adapt, to heal, and to find strength in engagement with the very forces that threaten them. We stand at a crossroads, equipped with technologies the ancients could never dream of, yet facing a timeless challenge: how to build a world meant to last. The answer may not lie in inventing a new super material from scratch, but in rediscovering the profound wisdom already written in the walls around us. So let us move beyond simple admiration for these enduring monuments. Let us become students of their quiet logic. Look at the ancient structure that amazes you most, whether it is the soaring dome of the Pantheon, the precise stonework of, or the serene curve of a Roman aqueduct. In its persistence, see not a mystery but a message about patience, about locality, and about building in conversation with time. Share which one speaks to you in the comments below, and subscribe to join us as we continue to unravel the profound mysteries of our past, not as relics, but as guides to building a better, more enduring tomorrow.